Hey, good morning, everyone. And my name is Huang from AMD Linux GPU team, and focus on multi-components, including the Linux kernel and AMD GPU, kernel graphics, compute, DRM, and CPU power management support over 10 years. And I'm new for Xen, and this is my first time to join and present talk in the Xen Summit. So it's my great honor to have opportunity to talk about the VirtIO GPU and Passthrough GPU here to all of you. Yeah. And these are the team members we are working for the support, and they are come from two different countries in the world, except the Xenier, and we are all new for Xen area. Yeah. And I'm very happy to Xenier is here today, who is one of the key members of the program, and also appreciate Stefano for the great support all the time. And we are working closely together to deliver these solutions. And today, I would like to go through for sharing with overall design and the implementation. And for these solutions, in fact, it is a long time since we prepared solutions at about middle of last year. These are multiple components, including the Linux kernel, then QEMU, Mesa, and the Virglrenderer. And we spent quite a few months to resolve some issues, support QEMU and Xen, but some of them are fixed by the workarounds, and but still not root cause yet. Anyway, we already rebased to the latest version and of the Virglrenderer and Mesa part, and will submit to the QEMU. Then kernel V2 version changes very soon. And Vulcan, if you have any review comments, and for us, and feel free to interrupt me if you have any questions. Okay, move to the intention. And we are working to deliver the support for the automotive infotainment system. We already have multiple. We already have a complete graphics on the bare metal platforms in the existing automotive system. In that system, we have the open graphics libraries, including the OpenGL and Vulkan, and support with the native AMD GPU drivers, Mesa drivers such as the Radeon SI and RedV. RedV is the Radeon Vulcan for the production. And however, the bare metal solution is not satisfy the needs of the modern automotive systems because the requirement of the multiple systems in one car. So we are designing and developing the Xen-based GPU virtualization right now. Xen is one of the most popular hypervisors in the world and widely used by the automotive system and the embedded platforms. And we are developing the 3D graphics, multimedia hardware accelerations for AMD GPUs and CPUs. And this is the existing situations of GPU virtualizations on Xen. The VirtIO GPU is designed to emulate a hardware device in the QEMU. And this can be enabled on the Xen platforms, but only the Virgl, which is OpenGL support for VirtIO GPU, can be used. And this support is not even fully verified on Xen. So because we still find quite a few issues on the existing the VirtIO GPU support with the Virgl. And another, Vulcan is advanced standard 3D open source graphics libraries. It is required by a lot of modern 3D applications and games right now. The graphics support cannot be without Vulcan right now. And AMD GPU is only able, but for in current Xen platforms, we cannot have the Vulkan support. Yeah, there is no Vulkan. And AMD GPU is only able to support Xen PV DOM 0 for all the PCIe device, including the AMD GPU. However, in GPU user scenarios, there will always have many large size of data buffer copies, as such as the gigabytes, megabytes, and gigabytes on the device for the video memory and the frame buffer. And the software IOTLB is only handled by the buffer page by page, buffer support, copy page by page. It is not can be usable for the GPU case. So currently, the PCIe pass-through and another. This is one case we on the existing platform, and another is PCIe pass-through is only support for the PV DOM 0, as Roger mentioned just now. We all know the GPU pass-through is also very popular user case for virtualization. So it's we have to we can only able to map one GPU device in one guest DOM-U. So above all, there are the current situations for the GPU virtualization on Xen. And yeah, okay. Then we design and implement the new proposal to improve the GPU virtualization according to the shortage on Xen one by one. And in graphics stack, we are improving the OpenGL support in the guest DOM-U, which is able to resolve the issues for each graphics test case. And the most of important step, we need to add the Vulcan support in the guest DOM-U. That means we need to enable the Vulcan driver for the VirtIO GPU. And the Vulcan driver is developed by the Google. They are already used on the Google, the Chrome OS platforms. You know, the Chrome OS is use another virtual machine. We call it Cross VM. And then Cobra port the changes from Cross VM to the QEMU on KVM. Then we pick up the KVM support on the QEMU, and then we make it work on the Xen platforms. But it's not upstream yet, and we are leverage that implementation and design, and we resolve quite a few problems and finally get workable on Xen, and we can run most. So far, we can run most of the graphics applications, benchmarks, and the Steam games right now. And later, I will give a demo to run the Vulcan Steam game in the Xen guest after the introduction. And to address the Xen software IOTLB, the shortage platforms, the problems on GPU, I discussed with Roger and Stefano, and we decide to use the PVH DOM 0 for our x86 processors. And at the same time, we add all new support for the PCIe pass-through functions on PVH DOM 0. Let's first try, and we leverage QEMU firstly. Maybe next step after the QEMU can be accepted, then we will try the VPC and leverage the support from the steward in the ARM. Yeah, we may work together in the next step. And our target is to support AMD GPU device in the backend. You know, the GPU is only the one is one of the PCIe function device. So in one guest, we probably have two types of GPU support in a guest. One is a VirtIO GPU, it's the virtual GPU. Another is a pass-through AMD GPU. Then we will talk the transaction between the two types of the GPU together. Yeah, yeah, I will talk it later. And let's look at the overall design of the Xen GPU virtualization. We have several guest OMMU in the system, and they already use a different Linux Linux system. We have Android, we have Ubuntu Linux, and we mainly works on the Ubuntu Linux graphics support. The Ubuntu Linux is using the Xen X server and the VLAN, the X Windows system to talk about DRI interface, which is front end use the Mesa, and we will go with the Mesa GPU driver, including the Virgl and Venus, and the Radeon SI and the RedV. And the Virgl is open. Virgl is the OpenGL driver for the VirtIO GPU, and Venus is the Vulcan driver for VirtIO GPU, and RedV is the Radeon Vulcan driver for AMD GPU, and the Radeon SI is the OpenGL driver for AMD GPU. So each single GPU we have a different driver to attach it in the Mesa 3D graphics, like that for the usable space driver. And Zink is the OpenGL on Vulkan translation layer. We can even use the Zink plus Venus instead of the Virgl. But after testing, we found the Zink's performance is not good as expected, so we drop it. And the name we call is the libdrm interface and to the kernel DRM VirtIO driver, and we support two kind of the virtualization. One is VirtIO GPU, and they can be used to the different multiple virtual machines, and we also we can send VirtIO command to the QEMU, and the QEMU will decode the VirtIO GPU command and access the Virglrenderer. And then once we get the GPU command in the Virglrenderer, we can decode it and access the GL and the Vulcan the functions which based on the host Mesa stack. Now we can connect the guest graphics stack and to the host graphics stack with the Virglrenderer and QEMU. Yeah. And another list is to implement the hardware accelerations for the virtual GPU. And another is the Passthrough GPU. We are using the PCIe back driver in the DOM0 to respond to hypercore from Xen and map it the PCIe config space, MMIO bar, and interrupt from host to guest. So in our platform, we are using the iGPU for VirtIO GPU and the discrete GPU for the pass-through. They will work together in one guest VM. And let's talk about the details for the GPU pass-through on the PVH DOM0. And yes, this is my first try to implement functions for Xen. So we leverage the QEMU to implement PCIe pass-through. Our intention to pass through the discrete GPU device from one guest VM DOMU, and we can have a powerful 3D capability in the guest, and kernel, the kernel AMD GPU driver, the native Radeon OpenGL driver, and the Vulcan driver can be supported in the guest at this moment. We compare with the pass-through support on the PV DOM0. Then leverage that kind of support to implement, to use the kernel Xen PCIe back driver to attach the device of the GPU in DOM0 This is avoid the GPU device to be attached in the native AMD GPU driver. Then the device can be passed through into the guest. And use we introduced the setup, the interrupt, as Roger mentioned. We add the setup GSI interrupt because we found we have some issues for the MSI interrupt on the PVH DOM 0 yet. So we use the traditional the legacy interrupt firstly to set up the GSI, and we need to introduce the PCIe device reset messages and the memory mappings for in the hypervisor core to transfer the request to DOM-U, then bring up the Xen pass-through functions and to map the PCIe config space register ranges and interrupt IRQs. Let's assign the PCI device totally into guest DOM-U, and the amdgpu pass-through device can be shown in one of the guests and enable the native graphics driver stack here. And there are many behaviors we do the pass-through on PVH DOM 0, and they are still under the code review and not finalized yet, because we are working on other agent issue to enabling the VirtIO GPU, so we didn't have a chance to finish the V2 version yet. But for now, we will try to enable it after conference, and we will post the V2 version very soon. And so current design, this is first used at PCI function reset message according to the suggestion from the Roger, and to resolve the PCIe the PCI back driver cannot info the VirtIO bar status in the Xen hypervisor. That means once we do reset, but the bar in the Xen hypervisor, they don't know we already do the reset in the DOM 0. So we have to use the reset message to info the Xen hypervisor. And then we map to the I/O port and the I/O memory with these two messages for on Xen. We the many modifications on PVH is to map the pass-through interrupt. We found the MSIX and the MSI issues on the pass-through device for the guest VM. Our guest VM is used the HVM, and the DOM 0 is used the PVH. So we need to we need to set up the bridge between the GSI interrupt IRQ and the PIRQ and bind the event channel to the guest. And later is proposal to implement the PCI pass-through for the Xen PVH DOM 0. And I submit a design section. Maybe we can discuss more the issues regarding to the PVH DOM 0 and in later this afternoon. And let's take a look at the flow of VirtIO GPU on Xen. We have multiple GPU virtualization solutions on AMD GPU. In previous time, SRV is always used by the data center GPUs. That requires the hardware firmware support to separate one GPU in multiple virtual functions. But few of several GPU can support it. We have to we had hardware limitations. The VirtIO GPU's way can support hardware accelerations in the software way. We are used the QEMU to emulate a virtual GPU for the guest DOM-U, and the VirtIO PCIe driver can be attached to the VirtIO GPU in the PCIe virtual device, and load the VirtIO kernel DRM driver, and the virtual GPU device is emulated by the VirtIO bus, and the user space implemented with the OpenGL and Vulkan driver for these virtual GPUs. And adding GPU operations can be mapped by the VirtIO GPU commands to issue the host QEMU, and then the QEMU use the Virglrenderer command to separate different contexts from the Virgl and the Venus. The Virgl is a command from the OpenGL, and the Venus is commands context from the Vulcan driver. Now we can assess the different context to assess the GL and the Vulcan functions. In other words, this is the Virglrenderer is a specific OpenGL and Vulkan applications in the host. Then they can access the host Mesa, OpenGL and Vulkan driver, and then VirtIO GPU in fact is also a hardware accelerate GPU in the backend. Okay, as mentioned in the last page, we have multiple Mesa driver in different GPU, including the VirtIO GPU and the native AMD GPU. It's similar with the. I would like to introduce the similar video memories. Let's VRAM start for the VirtIO GPU. In HVM configurations, we are using the bulk memory. The bulk memory is the host memory for the guest VM, guest GPU. Let's reserve a piece of the host memory window here in the kernel VirtIO driver, and later expose one of the large MMIO bar in the guest PCIe functions. Let's reserve for the guest Mesa driver access. Then the guest OpenGL driver, they have their own video memory can be accessed for the GPU applications. Then the Mesa driver can access that memory directly. In host DOM-U, we expect to use the QEMU bulk operations functions such as create and map to implement a direct mapping into the host shared memory and the DMA bar. The shared memory is the host CPU system memory, and the DMA bar is used for the memory, will be used for the GPU access. I also will discuss the design, this kind of different page tables in the GPU and the different page tables for the CPU. Then how to work together in the design section. Then we found the direct mapping issues on the PVH DOM0. Then for the direct address mapping. For the bulk memory, and Xenier and I made this workaround to use pinning buffer solutions for the bulk memory. That should be a workaround, but cannot be for the final solution. So we can talk more about the problem in the afternoon and for the bulk memory direct mapping issues. Yep. And okay, and in real system, we also implement the multiple display into the physical screens, and we implement S3 suspend resume. This is very important functions and system, and because the guest DOM-U can be suspended at runtime and disconnect physical display and save power. In the real system, each guest VM we will map into the physical device in the automotive system, so we can do the suspend resume in one of the guest VM, then disconnect the monitor in a car. Then they can save more power in this kind of use case, and we need to keep the resource. And after we implement the callback functions of freeze and restore. And we need to keep the resource cannot be destroyed in the suspend time, and to make sure in the freeze it can enforce the QEMU to delete the virtual queues and have to keep the resource alive. And once the QEMU is responding the resume, and it will use the result source to mapping the VM again. So we already start to upstream the S3 patches and hope any comments for any review comments is welcome. And we have we just talk later. We already have two types of GPU in the guest DOMU. One is VirtIO GPU, another is Passthrough GPU. We are fully leveraged the two GPUs render capabilities. They're running on the heavy 3D workload, so we can offload the Passthrough discrete GPU for rendering and use the VirtIO GPU for display. So all the we can if the heaviest applications Steam games, we can in the Ubuntu Linux we can use discrete GPU, Passthrough discrete GPU for rendering, and then the picture can be composed into the guest compositor for the display on the VirtIO GPU. So we will leverage the DMA bar to export and import the display resource between the Virgl and the RadiusSI driver. Let's do different OpenGL driver to implement the buffer sharing, and then the DGPU resource can be composed in the guest DOM 0 compositors for QEMU display. At least we already submit the code into the free desktop. If you have an interest, you can access the Xorg Foundation's community review. There is another GitLab for review all the graphics patches. And we also support the same functions for the Vulcan. That's a bit different with the OpenGL implementation because the resource buffer sharing during the RedV and the Radiant Vulcan driver and the VirtIO GPU the Vulcan driver, and the Mesa will link the GBM and to the Venus and to create this buffer for sharing. That's different with the OpenGL. We will add a foreigner GBM allocations in the display buffer for swap chains, and we also encounter issue for stride, and we are working with the Clubra and to dig out the root cause of this. Okay. Besides the graphics support, we also introduced the VirtIO video support. And for our GPU, that's different with the VirtIO video. The VirtIO video is leveraged to V4L2, the kernel device driver framework to implement the virtual GPU device in the guest VM. However, we are different because AMD's GPU, AMD's video function is inside of GPU, so we need to leverage the GPU Mesa driver to implement the VAPI front end in the Mesa driver and implement the video hardware virtualizations in the Virgl OpenGL driver and for the VirtIO GPU. And the video player such as the MPV, FM pack can be accessed the VAPI interface, which is the Virgl video as the backend. And then the video command can be issued from the guest Virgl video and to the host Virglrenderer. In fact, we already add the video render in the host as well, and then the host and then host Radiant VCN driver. VCN is a hardware engine inside of AMD GPU hardware. They will execute the multiple encoder and the decoder on the different codec. So far, we already support the VP9, VC1, MP Giga4, JPEG, and MP Giga2, and blah blah. There's some popular encode and decode codecs. In Virgl video, the implementation is already under code review, and we are close to be accepted right now. And this is the video workflow let's hold the guest video in the Mesa to talk about the hoster and the VP APIs. Once the VM start, the VP initialization of the applications in the VM is handled by locally. Then when the VM create a VA surface, and the host will create a VA surface accordingly. And when the guest VM performing the decoding to the first time, and the VirtIO video will create a true configs and the context for the list video codec in the host. Then the VM will cause the render pictures, and the Virgl will start the real decoding process in the host at that moment. As we know, the workflow how the guest the Mesa video to talk about the hoster, and then we will talk about the video data transfer in the host QEMU. Now we can use all the host VP API to decode them in the real hardware. Then the VM calls the VA create surface, and then the host will create the VRAM resource according to the destination for decoding. Then the VM start decoding a frame. It's copy the video data to the host to map according to a map method. After decoding, the host can convert the result to the texture for the VM display. So, okay, let's talk about, we already do quite a few OpenGL tests in the graphics bench, Unity Volleyer, and CSGO, and Mad Max. Let famous the thing game and benchmark for the OpenGL, and this is the data we assign to the first the percent please look at the OMMU Virgl. Sorry. Please look at this column. And this is the OMMU divide by the DOM0. So the 50% to the 90% compare with the DOM0. This is the current performance. We still have a room to implement the guest performance for the OpenGL. And let's continue look at the Vulcan test. We have the graphics bench, the Vulcan, the normal, and the famous 3D Mark, wildlife. This is also required by the graphics function of the graphics area, and we also support Dota 2 and the rise of the Tomb Raider. And this is the data. We try to the famous benchmark, and the performance is also the 50% and to the over 19%. And we still need to improve the performance. Next step for compare with the DOM0 and the bare metal. We found the DOM0 is close to the bare metal. It's very close to the bare metal. That's the PVH DOM0. And we also try to try the video test case to do the FM pack and some popular the video codecs. And we didn't have the data for the video for now, and hope in next time I will give the video data. Okay, and finally we are working on the develop the VirtIO native content, and with AMD GPU on Xen at this moment. This design is initialized by Google late of last year. So they are used the native content method to forward the native DRM API to the guest method directly with the Virglrenderer. So use this way, we can use native method driver instead of Virgl and Venus it's more straightforward and performance way. And Google also prototype this kind of design in a Qualcomm GPU for Chrome OS. So we leverage their design to implement the AMD GPU on Xen, and it will be coming very soon. And we also need to provide a formal solution to resolve the direct mapping issues on the in the virtual MMIO bar for the QEMU on Xen at Bob memory. So far, we are using a pinning buffer solution, for workaround, and we plan to use a MMU notifier to update page table at backend dynamically, and we also need to do the fully graphics benchmark verifications on the current solutions. And the GPU is not only for the graphics area. There are more. The more important user scenario for GPU is a compute support, and for AI area, the machine learning, we would like support the AMD Vulkan compute stack at gas VM for VirtIO GPU, VirtIO native content, and then we can have OpenGL, we can have heap, we can have more and more machine learning stuff in the gas DOMU as well. We can run the TensorFlow and something else, the AI framework. All right, we are happy to have an opportunity to improve the GPU virtualization on Xen. Yeah, I believe this is just a start, and we will continue to improve the Xen GPU virtualization in following days. Okay, that's the reference so far. If you want to try our source code, and you can pick the AMD Ryzen 4000 series APU. That's the first prototype on Lattice APU. Yeah, you can. It's very cheap. You can just purchase a laptop, and then can try the Xen GPU solution. Of course, we will try to support more and more all the GPU device in next step. So far, because of the time, aggressive time schedule, so far the 4000 series is suggested. Okay. Before that, I can give a video recording demo. Sorry, I'm over time. For that, yeah. I cannot bring the device here, so I just a big video recording to enable the QEMU, enable the HVM, and the PVH is on DOM 0, and DOM U is HVM guest. Yeah. So this is the Vulcan famous Vulcan cube applications we are used there.
With VirtIO or with a physical PCI pass-through card?
VirtIO, not pass-through. So you will see the VirtIO GPU here. Yeah. Let's run the Steam game. It's in a APU laptop. So even the APU laptop, the performance is good. Yeah, let me continue to look at the Steam game, Tomb Raider. Yeah.
I'm really sorry, but we've actually run over time.
Oh, sorry. 1 minute to finish the video. I'm sorry. Yeah, you will see this is the VirtIO device Vulcan driver. The backend is Radeon graphics. Then we can start the video, the gaming benchmark here. Yeah. This is time frame. Yeah. Yeah. So any comments and questions, we will have a design section. Feel free to ask me, and we are engineer Stefano, and I were in that design section also. Roger is here.
Thank you.
Okay, thank you. so much.